Here we have the graph of the function sine of x all over x. Now x is in radians. As a reminder, if x radians is the angle in this sector of the circle, it is defined to be the number of times the radius of the circle fits into the arc subtended by the angle. So x is the length of the arc L divided by the radius. Notice that for large positive values of x, the graph appears to be approaching the x-axis, and that's also true actually for large negative values of x. Now the sine function is always a number between -1 and +1. So when we let x get larger and larger, either by making x a very large positive value, or indeed we could make x a very large negative value, so we could have let x tend towards plus or minus infinity here, this denominator is going to increase, but of course that will have the effect of making the entire function go to 0. So the entire function will go to 0 because sine of x on top is always between -1 and +1, so that's always some finite value. So if we blow up the denominator, the entire thing is going to go to 0. So we can let x tend towards plus or minus infinity. So that explains the graph. Well, it explains the graph for large positive values of x and large negative values of x. Another thing I should mention is that the graph is symmetrical about the y-axis. In other words, if we get f of 2, we will get the same value as f of -2. For example, let's suppose we want to get f of -2. Well, we have to get sine of -2 and divide by -2. But the sine of -2 is minus sine 2. Okay, that's true in general. The sine of minus a, where a is any angle, is minus sine a. These two minuses cancel, so we get sine 2 over 2. But sine 2 over 2 is f of 2. So we see that f of -2 is the same as f of 2. And of course, in general, f of minus x will equal f of x. A function with this property is called an even function. It is symmetrical about the y-axis. Now we are mostly going to be interested in this function in the neighborhood of x equals 0. Here we have a table of values of f of x for values of x ranging from minus 0.5 towards 0. We're going up here in steps of 0.05. Notice that these values appear to be approaching a limit. What about the value of the function at 0? Well, if we try to work this out by plugging 0 in for x, the sine of 0 is 0. We get 0 divided by 0. Now we saw in a previous video that 0 divided by 0 is indeterminate. We can set it equal to any number we like. We could set this equal to 2.78, and this will still work out because if we cross multiply, 2.78 times 0 will give us 0. So it doesn't actually matter what value we have here. We could have minus 1.3. So we saw this kind of thing in a previous video. So it appears that this function isn't even defined at 0. To show that, we can circle out 1 on this axis here, because it appears that as x approaches 0 from the left at least, f of x is approaching 1. And that is indeed the case. And we can also look at what happens when x approaches 0 from the right, starting with 0.5. So we're approaching 0, but we never reach 0. We can see that these values appear to be approaching +1. As a matter of fact, these values are the same as these values, because we saw that f of a negative value is the same as f of the corresponding positive value, because we have an even function. So it appears that the function sine x over x is getting closer and closer to 1 as x approaches 0. In other words, we can make sine x over x as close to 1 as we like by taking x sufficiently close but not equal to 0. And it works from both sides. So this statement appears to be true, but we're going to actually prove this not by looking at a graph, which isn't really a proof, but by considering a geometrical construction. Angle X is constructed in a circle of radius r. By comparing the area of triangle ADC to the area of the sector ADC and also the area of the right angle triangle ADE, we can actually find the limit as x tends towards 0 of sine x over x. So the area of triangle ACD, that's the red triangle, is less than the area of the sector ACD, which in turn is less than the area of the right angle triangle ADE. Now to get those areas, let's start with the small triangle. We know from trigonometry that if we have two sides of a triangle and the angle in between, we can get the area by getting half the product of the two sides by the sine of the angle in between. So if the two sides are equal to r and the angle in between is big X, then we have a half r times r sine big X. So that's our half r squared sine x. So that's triangle ACD. Now let's look at the sector ACD. Well, to get the area of a sector, we take half the radius squared times the angle in the sector in radians. So you can easily prove this if x is in radians. If x is in degrees, this is not true. Now finally we have triangle ADE. This triangle is constructed by drawing a tangent to the circle at point D. Now it's a fact that the line from the center of a circle to the point of contact of a tangent is perpendicular to the tangent. To get the area of this right angle triangle, we are going to get this side of the triangle. So this will act as our perpendicular height if we take r as base. Well, the side opposite x is what we're looking for. Let's call it h. So the tan of x is the side opposite x, which is h, divided by the side adjacent to x, which is r. So from this we see that h equals r multiplied by tan x. Because we have a right angle triangle, we can easily get the area by using the formula half the base by the perpendicular height. So if r is the base, the perpendicular height is r tan x. So we have a half r times r tan x. That gives us a half r squared tan x. So no matter how small we make x, and we will be letting x tend to 0 to get our limit, these areas are related like this. Okay, let's work with this. We want to try and get sine x over x. We're going to try and get that ratio from this inequality here. So we can start by dividing everything by a half r squared. Why can we do that? Well, a half r squared is positive. The radius of the circle is certainly greater than 0, and when we square it, it's certainly positive. So we can divide everything by a positive quantity, and that doesn't affect our inequality. So we end up getting that sine x must be less than x, which in turn must be less than tan of x. This is provided x is in radians. Now, we are dealing with positive value of x here. Value of x that's only slightly greater than 0. So the sine of x will be positive and the tan of x will be positive. So these three quantities are actually positive for x greater than 0. Well, x is not that much greater than 0, so we don't have to worry about sine and or tan being negative. We can invert these three quantities since they're positive numbers that are related like this. So we get 1 over sine x when we invert sine of x. When we invert x, we get 1 over x. Now, tan of x is the same as sine x over cos x. So I'll write it like that. So if we invert this, we get cos x over sine x. Now to see what happens, let's consider a very simple inequality, 1 less than 2 less than 3, and let's invert these three numbers. If we invert 1, we get 1. If we invert 2, we get a half. If we invert 3, we get a third. And notice that we have to switch the direction. 1 is greater than a half, and in turn a half is greater than a third. And that's exactly what we must do here. So we've three positive numbers here, just like 1, 2 and 3. And when we invert them, we have to change the direction of the inequality. Now remember, we're looking for sine x over x, and to get sine x over x we just need to multiply this inequality by sine of x. Now since x is a positive quantity, sine of x will also be positive. Again, x is a number that's not much greater than 0, so we're dealing with just a positive x, so its sine will be positive. Of course, if we deal with values of x that are, you know, between 180 and 360, then it's a different story, but we're dealing with acute angles, angles that are close to 0 but are positive. So we don't have to worry about the direction of the inequality when we multiply by sine of x. So we're multiplying all of this inequality by positive quantity. Now the sine of x times 1 over sine of x will give us 1. The sine of x times 1 over x will give us what we're after, which is sine of x over x. And sine of x times this thing here will give us cos of x. The sine of x cancels. For convenience we can turn this around. I can read this from right to left. Cos of x is less than sine of x over x, which in turn is less than 1. Now we are going to see what happens to sine x over x as we make x go to 0. So on the next line we have the value of cos of x, that's the cos of this angle here. Then we have the value of sine x over x. Okay, let's see what happens as we make x go to 0. Well, cos of x is actually approaching a limit. That limit is actually 1. Cos of x approaches 1 as x approaches 0. In other words, we can make cos of x as close as we like to 1 by taking x sufficiently close to 0. The limit as x tends towards 0 of cos of x is just cos of 0. We only have to plug 0 in for x for this function. The cos of 0 is 1. So this number here is approaching 1, but we can see that it's always less than sine of x over x, which in turn is always less than 1. So we can take the limit as x tends towards 0 of this inequality, just like we saw. So this is something that we can do. I'm not going to prove why we can do this. You can just take this for granted. Intuitively it makes sense. Since this thing is equal to 1, we see that 1 is less than the limit as x tends towards 0 of sine of x over x, which in turn is less than the limit as x tends towards 0 of 1. Now we're taking the limit of a constant here, and the limit of a constant is just a constant. So we can think of 1 as a constant function. So this is what we're after. We see that it's greater than 1, but it's also less than 1. So this thing is squeezed between 1 and 1, so it must equal 1. The only way that it can be greater than 1 and less than 1 at the same time is if it's equal to 1. So that's what's happening. This number is approaching 1, but this number is always less than this number, and this number in turn is always less than 1. So this number here is also approaching 1. So we saw that this inequality holds. Now we can actually invert this inequality and see what the limit of this function is as x approaches 0. So this function is got by inverting the function that we are interested in. Why can we invert these? Well, they're all positive, because remember x is greater than 0. It's some small number greater than 0. And when we invert, we must change the direction of the inequality like we saw before. Now it can be proven that if we have an inequality, we can take the limit of each term in the inequality. Intuitively that makes sense, like we saw before. Now what is the limit as x tends towards 0 of 1 over cos of x? Well, actually, to solve this we only have to plug 0 in for x, because this is a continuous function. There are no breaks in it, and that won't lead us into any trouble. So we get 1 over cos 0. Well, that's 1 over 1, which is 1. Over here we have the limit as x tends towards 0 of a constant function. So this is just, so the answer will just be 1. So we see that 1 is less than this quantity, but this quantity in turn is less than 1. So it's squeezed between 1 and 1, so it's equal to 1. So we've seen that as x approaches 0 from the right, because we're dealing with positive x, our function sine of x over x is approaching 1. And by symmetry, the same is true on the other side. If we took negative values of x less than 0, and let x approach 0 from the left, f of x would also approach 1.